As both aldehydes and ketones contain the carbonyl group, they resemble each other closely in most of their properties. The carbonyl group governs the chemistry of aldehydes and ketones in two ways: by providing a site for nucleophilic addition and by increasing the acidity of the hydrogen atoms attached to the alpha carbon. Both of these effects are due to the ability of oxygen to accommodate the negative charge. The typical reactions of aldehydes and ketones are nucleophilic addition reactions. Before we examine the different types of nucleophilic addition reactions, let us first understand the general mechanism of nucleophilic addition reactions. The first step is a slow or the rate-determining step, which involves the attack of a nucleophile on the electron-deficient carbonyl carbon. Since the carbonyl group is flat, it is liable to be attacked from above or below the planar carbon atom. As the nucleophile forms a bond with the sp2 planar carbonyl carbon atom, the electron pair of the carbon to oxygen pi bond shifts to the carbonyl oxygen. The carbonyl oxygen easily accommodates the electron pair to produce a tetrahedral sp3 alkoxide ion intermediate. In the second step, the alkoxide ion captures a proton from the reaction medium to give an electrically neutral tetrahedral product. If the nucleophile is strong, it will readily attack the carbonyl carbon. The resulting addition product can be readily protonated by the solvent or by the added acid. However, if the nucleophile is weak, then it requires an acid catalyst to make the nucleophilic addition reaction occur at a reasonable rate. The acid protonates the carbonyl oxygen to produce an oxonium ion. The oxonium ion is highly reactive towards nucleophilic attack at the carbonyl carbon atom. This is because the carbonyl carbon atom carries more positive charge than it does in the unprotonated compound. The addition of alcohol to the carbonyl group is an example of acid-catalyzed nucleophilic addition. The reactivity of the carbonyl group towards nucleophilic addition depends mainly upon the magnitude of the positive charge on the carbonyl carbon. That is, the electronic factor and the extent of crowding around the carbonyl carbon atom in the transition state. That is, the steric factor. Based on these factors, the order of reactivity is formaldehyde without any alkyl group is more reactive than other aldehydes with one alkyl group, which, in turn, are more reactive than ketones that contain two alkyl groups. Electronically, alkyl groups are electron-releasing groups that release electrons and stabilize the carbonyl carbon by reducing the magnitude of positive charge on it. Hence, the electrophilicity on the carbonyl carbon, and therefore the reactivity, decreases with an increase in the number of alkyl groups. Sterically, the presence of bulkier alkyl groups in ketones hinders the approach of the nucleophile towards the carbonyl carbon. Hence, the bulkier the alkyl group, the lesser is the reactivity. Therefore, the decreasing order of the reactivity of ketones is acetone is more reactive than ethyl-methyl ketone, which is more reactive than isopropyl methyl ketone, methyl tertiary butyl ketone. An aryl group has an electron withdrawing inductive effect, So, it is expected to destabilize the reactant and speed up the reaction. However, it seems to stabilize the reactant even more by resonance, and thus decreases the reactivity. Thus, propanal is more reactive than benzaldehyde because the polarity of the carbonyl group is reduced in benzaldehyde as shown. Now let us look at some important examples of nucleophilic addition on the carbonyl group. These include addition of hydrogen cyanide, addition of sodium bisulfite, addition of Grignard reagent, addition of alcohols, addition of ammonia and its derivatives. When hydrogen cyanide is added to the carbonyl group of aldehydes and ketones, it yields compounds known as cyanohydrins. As HCN is a very weak acid, it is a poor source of cyanide ions. Hence, addition takes place very slowly. Therefore, the addition of a base can generate cyanide ions from the weak acid, HCN, causing a dramatic increase in the rate of the reaction. The cyanide ions, being stronger nucleophiles, rapidly attack the carbonyl carbon to produce the corresponding cyanohydrins. Cyanohydrins are useful intermediates in organic synthesis. They undergo hydrolysis to yield alpha-hydroxy acids or unsaturated acids. For example, the addition of HCN to acetaldehyde yields acetaldehyde cyanohydrin, which, on hydrolysis, yields lactic acid or alpha-hydroxypropanoic acid. Let's look at the addition of sodium bisulfite. When sodium bisulfite is added to an aldehyde or a ketone in the presence of ethanol, it gives a water-soluble solid adduct. This solid adduct is filtered from ethanolic solution and then decomposed by an acid or a base to regenerate the carbonyl compound. Hence, this reaction is used for the purification and separation of carbonyl compounds. For example, acetaldehyde reacts with a saturated solution of sodium bisulfite to give a white crystalline precipitate of acetaldehyde sodium bisulfite. Yet another addition reaction is the addition of a Grignard reagent to the carbonyl group. In this addition reaction, when a Grignard reagent, RMGX, is added to the carbonyl group, with its organic group R being attached to the carbonyl carbon and magnesium to the carbonyl oxygen, it produces an addition compound, which on hydrolysis yields an alcohol. As you can see, formaldehyde produces a primary alcohol, a secondary alcohol with the other aldehydes, and tertiary alcohols with ketones. This relationship arises directly from our definitions of aldehydes and ketones, and our definitions of primary, secondary, and tertiary alcohols. Aldehyde reacts with alcohol in the presence of anhydrous hydrogen chloride to form an unstable intermediate known as hemiacetal. Hemiacetal further reacts with one more molecule of alcohol to give a gem dialkoxy compound known as acetal. This reaction is an example of acid-catalyzed nucleophilic addition in which dry HCl gas protonates the oxygen of the carbonyl group so that the oxonium cation formed is more susceptible to nucleophilic attacks. All steps involved in the formation of acetals from an aldehyde are reversible. Ketones react with an excess of ethylene glycol under similar conditions to form cyclic products known as ethylene glycol ketals. Both acetals and ketals can be rapidly hydrolyzed with aqueous mineral acids, even at room temperature, into aldehydes and ketones respectively. Let's now look at the addition of ammonia and its derivatives. When nucleophiles, such as ammonia and its derivatives, NH2G, are added to the carbonyl group in the presence of acid, they form compounds with carbon to nitrogen double bonds, known as imines. Let's understand the mechanism of this reaction. 1. Initially, the hydrogen ion from the acid attaches itself to the carbonyl oxygen to produce an oxonium cation. 2. This is followed by a nucleophilic attack by the basic nitrogen on the carbonyl carbon to form an intermediate addition product. 3. Further, the elimination of the water molecule from the intermediate results in the formation of the product with the carbon to nitrogen double bond. Since these reactions involve the addition of a nucleophile in the presence of an acid followed by the elimination of the water molecule, they are termed as nucleophilic addition-elimination reactions. Aldehydes and ketones react with ammonia derivatives with the general formula NH2G. Here, G is equal to R, alkyl group, OH, NH2, NH, C6H5, NH, CO, NH2, etc. Aldehydes and ketones react with primary amines to form substituted imines, a Schiff's base. Aldehydes and ketones react with hydroxylamine to form the corresponding oximes. For example, acetaldehyde and acetone react with hydroxylamine to form acetaldoxime and acetoxime respectively. Aldehydes and ketones react with hydrazine, NH2NH2, and its derivatives such as phenylhydrazine, 2,4-dinitrophenylhydrazine, and semicarbazine to form the corresponding hydrazones. For example, acetaldehyde and acetone react with hydrazine to form acetaldehyde hydrazone and acetone hydrazone respectively. Similarly, they react with hydrazine derivatives and form the corresponding hydrazones as shown in the equations here. Hydrazones are usually insoluble solids with sharp melting points. Moreover, oximes and hydrazones, when refluxed with dilute hydrochloric acid, regenerate the parent aldehyde and ketone. Hence, oximes and hydrazone are used for the detection and purification of organic compounds that contain the carboxylic functional group, COOH, are called carboxylic acids. The name carboxyl is derived from the carbonyl group C double bond O and the hydroxyl group OH of which it is composed. Carboxylic acids are widespread in nature. Higher members of aliphatic carboxylic acids, known as fatty acids, are important components of the biomolecules, such as lipids, fats and oils. Aliphatic carboxylic acids have been known for a long time. A large number of them are known by their common names that refer to their sources rather than to their chemical structures. The common names for carboxylic acids are usually derived from Latin or Greek words that indicate the original source of the individual acid. All common names of these acids end with IC acid. For example, the name formic acid, HCOOH, is derived from the Latin word formica, which means red ants, while acetic acid, CH3COOH, is derived from the Latin word acetum, which means vinegar. Similarly, butyric acid is derived from the Latin word butyrum, which means butter. The name caproic acid, which is obtained from goat fat, is derived from the Latin word caper, which means goat. A dicarboxylic acid contains two carboxyl groups. The table here gives the common names of some dicarboxylic acids. Their names can be easily remembered by the mnemonic, "Oh my, such good apple." When it comes to substituted acids, the position of the substituent is indicated by the Greek letters alpha, beta, gamma, etc. The carbon adjacent to the carboxylic is assigned the letter alpha, the next carbon beta, the next one gamma, and so on. For example, two methyl groups substituted on the alpha and beta carbons in a 6-carbon carboxylic acid is named alpha-beta dimethyl caproic acid. Aromatic acids are named as the derivatives of benzoic acid, C6H5COOH. For example, compounds A and B shown here are named para-bromobenzoic acid and ortho-para-dinitrobenzoic acid respectively. Methyl benzoic acids are given the special names of toluic acids. For example, the compound shown here is named metatoluic acid. Now, let's look at the IUPAC system. In the IUPAC system, carboxylic acids are named by replacing the ending E of the corresponding alkane by OIC acid to form alkanoic acid. For example, the IUPAC name for carboxylic acid containing one carbon is methanoic acid, obtained by replacing the ending E of methane by OIC acid. Similarly, carboxylic acids containing 2, 3, and 4 carbon atoms are named ethanoic acid, propanoic acid, and butanoic acid respectively by replacing the ending E of the alkanes concerned by OIC acid. For naming the higher numbers, the longest chain containing the carboxyl group is selected, and numbering is done from the side of the carboxyl group, always giving it the number 1. For example, the compound shown here is named 4-methyl-hexanoic acid. For naming compounds containing more than one carboxyl group, the ending E of the alkane is retained, and the multiplicative prefix di, tri, etc. is added to the term oic acid. The The position of the COOH groups are indicated by Arabic numeral before the multiplicative prefix. For example, the compound shown here, which contains 3 carboxyl groups on the first, second and third carbons, is named propane. 1, 2, 3 tricarboxylic acid. In the IUPAC system, benzoic acid is named benzene carboxylic acid. Note here that the common name benzoic acid is also accepted as the IUPAC name. If side chains or substituents are present, then they are indicated by numbers, with the carboxyl carbon atom being numbered 1. For example, phenyl acetic acid shown here is named 2-phenyl ethanoic acid. Similarly, phthalic acid is named benzene 1,2-dicarboxylic acid. The name of a salt of carboxylic acid consists of the name of the cation followed by the name of the acid, with the ending IC acid being changed to 8. For example, the compounds given here are named ammonium formate and potassium 2,3-dibromopropionate, respectively. Carboxylic acids can be prepared by several different methods: oxidation of primary alcohols and carbonyl compounds, oxidation of alkyl benzenes, carbonation of Grignard reagents, hydrolysis of nitriles, hydrolysis of alkyl chlorides and anhydrides, hydrolysis of esters. Let us see how carboxylic acids can be prepared from primary alcohols and carbonyl compounds. Primary alcohols or aldehydes, on oxidation with oxidizing agents such as acidified or alkaline potassium permanganate, acidified potassium dichromate, or chromium trioxide in sulfuric acid, gives carboxylic acids with the same number of carbon atoms. For example, 2-methyl-butan-1-ol on oxidation with acidified or alkaline potassium permanganate gives 2-methyl-butanoic acid. Aldehydes can also be oxidized to the corresponding carboxylic acids, even with mild oxidizing agents such as Tollens reagent or Fellings reagent. For example, acetaldehyde is oxidized to acetic acid in the presence of Tollens or Fellings reagent. Ketones also give carboxylic acids on oxidation. However, ketones are oxidized only under vigorous conditions, such as strong oxidizing agents and elevated temperatures. Under these conditions, ketones form a mixture of carboxylic acids with a fewer number of carbon atoms, as shown here. For example, butanone, on oxidation with hot concentrated nitric acid, gives a mixture of propanoic acid and methanoic acid. One of the most useful methods of preparing an aromatic carboxylic acid is the oxidation of an alkyl benzene. Chromic acid or acidic or alkaline potassium permanganate is generally used for this purpose. It must be noted that irrespective of the length of the side chain, the alkyl group is entirely oxidized into a carboxyl group. For example, toluene or ethylbenzene on oxidation with acidic potassium permanganate gives benzoic acid. It is important to note that only primary and secondary alkyl groups are oxidized into a COOH group, while tertiary alkyl groups remain unaffected. For example, N-propylbenzene and isopropylbenzene are oxidized to benzoic acid in the presence of chromic acid or acidic or alkaline potassium permanganate, while tertiary butylbenzene undergoes no change under these conditions. In the presence of these oxidizing agents, even suitably substituted alkenes are oxidized to carboxylic acids. For example, but-2-ene on oxidation in the presence of acidified potassium permanganate gives ethanoic acid. Cycloalkenes, on the other hand, are oxidized to dioic acids under these conditions. For example, cyclohexene, on heating with acidified potassium permanganate, undergoes oxidation to adipic acid or hexane 1,6-dioic acid. The carbonation of Grignard reagents is another important method for the preparation of carboxylic acids. Grignard reagents react with carbon dioxide to form the magnesium salts of carboxylic acids. The free acid can be obtained from the salt by treating it with mineral acids. Grignard reagents can be obtained by the reaction of alkyl halides with magnesium metal in dry ether. The conversion of trimethyl acetic acid from tertiary butyl chloride is illustrated here. Did you notice that the acid formed by this method contains one more carbon atom than the alkyl halide? Thus, this method has the special advantage of increasing the length of a carbon chain. Hydrolysis of nitriles is another method for preparing the carboxylic acids. Nitriles, on boiling with aqueous alkali or acid, get hydrolyzed to the respective carboxylic acids. Aliphatic nitriles can be prepared by treating an alkyl halide with sodium cyanide in the presence of the solvent dimethyl sulfoxide. The synthesis of pentanoic acid from N-butyl bromide shown here illustrates the complete method. Note that the acids produced from the alkyl halide also contain one carbon atom more than the original alkyl halide. The hydrolysis of acid derivatives such as amides, acid chlorides, anhydrides, and esters yields carboxylic acids. Amides undergo hydrolysis on being boiled with a dilute acid or alkali. The hydrolysis yields carboxylic acid and an ammonium salt with an acid, and carboxylic acid and ammonia with an alkali. For example, acetamide, on being boiled with dilute HCl, undergoes hydrolysis to give acetic acid and ammonium chloride. On the other hand, when it is boiled with aqueous sodium hydroxide, it gives sodium acetate and ammonia. Acid chlorides, on hydrolysis, give carboxylic acids. For example, acetyl chloride, on hydrolysis in presence of water, gives acetic acid and hydrochloric acid. The hydrolysis of acid chlorides occurs readily in presence of an alkali. Hydrolysis in the presence of an alkali first yields carboxylate ions, which on acidification give the corresponding carboxylic acids. For example, when acetyl chloride is hydrolyzed with an alkali, it first yields acetate ions, which give acetic acid on acidification. Anhydrides give the corresponding acids on hydrolysis. For example, acetic anhydride gives acetic acid. Acid hydrolysis of esters directly gives the carboxylic acids concerned. For example, ethyl acetate, on boiling with a dilute acid, gives acetic acid and ethyl alcohol. Alkaline hydrolysis of esters, on the other hand, first results in the formation of carboxylates, which on acidification gives the corresponding carboxylic acid. For example, on boiling with aqueous sodium hydroxide, ethyl benzoate gives sodium benzoate and ethyl alcohol. Acidification of sodium benzoate gives benzoic acid. Having learned the different methods of preparation of carboxylic acids, now try to accomplish the following transformations. Benzyl chloride into phenyl acetic acid. Orthobromotoluene into orthobromobenzoic acid. Tertiary pentyl chloride into ethyl dimethyl acetic acid. The conversion of benzyl chloride into phenyl acetic acid involves an increase of one carbon atom. The conversion can be achieved by first treating benzyl chloride with sodium cyanide to yield phenyl acetonitrile, followed by hydrolysis with aqueous acid. This is a simple reaction of oxidation of the alkyl group. This can be achieved by the oxidation of orthobromotoluene in the presence of alkaline potassium permanganate. The conversion of tertiary pentyl chloride into ethyl dimethyl acetic acid also involves an increase in the carbon chain. This can be achieved by first treating the tertiary pentyl chloride with magnesium to yield the corresponding Grignard reagent. The Grignard reagent, on reaction with carbon dioxide followed by acid hydrolysis, gives ethyl dimethyl acetic acid.